Hello, my name is Gabrielle Taylor. I'm going to be doing homework 1, part A, part 1. So it says using a geometric argument for linear algebra, we're going to derive the relationship between A transpose times A times C is equal to A transpose times Y. For linear regression, where A is the design matrix and C is the vector of coefficients. So let's do our drawing portion of this. So let's say we have just a graph, right, of data, and this is our y data, right? So we have a data set and we have data points in the set, right? And we're going to be using linear regression to find like a best fit model for our data points. So let's say we have just data points over here, and over here, right? And we want to find the best fit model for that. So we can split this up on our x-axis as 1, and then 2.8, and then 3. And then we can have over here, we can have 1, 1.8, and then 2. So what we can do with this data is that our y data is going to be our y points. So our y data is going to be our y points, and we need to do our vectors of these to find an equation for this. So using our vectors, we can have our base data points. So it's 2, so it's going to be 2, 1.8, 1. Actually, this is going to be changed. I'm going to change these points so it fits what we learned in class. So this was 1.82, and then this was 2.83. So I'm going to do this differently so it fits into what we learned in class. And so then we have over here, we're going to have our y data, so 3, 2.8, and then 1. And then this is going to be times n, and then this is going to be our y model. So this is going to be our y model for our data points, for our y. So the next thing that we want to do is our x data points that we have here. So our x data points are going to be 2, 1.8, 1, and then it's like we're doing the line best fit, so we're going to be using that line equation. So we need m plus b, and then 1, 1, 1 for that. So after we have this, we can see that y model, we can combine. So for y model, we can combine these two base vectors, right? We can combine these two base vectors, so we get 2, 1.8, 1, 1, 1, 1, and then we're going to combine the coefficients as well. So then we have m and then b, and then from this we can see that this is going to be called our A, because this is our design matrix, and then this is our C. This is our base vectors of our coefficient, right? So we have our y model. Now let's just say we have a different one to expand on this further. So we have our y as well, and then let's say we have a point, we have a line coming through here, and then this is our 2, 3, and 1, right? So this is our data we were given. So let's say we have another y model, right? So we have 2, 3, 1, which is our ny model, right? And then from that we have C1, we have 0, 1, 0, and then we have C2, which is 1, 0, 0, 1, right? And so this is our data, and then from that data we're going to get our model. So we have this, I'm going to make this more longer here. Okay, so then this is our 2, 3, 0, right? And then in between these 2 points, you're going to get is this line here. So this line here is going to be our error, right? And this is perpendicular. So this error is perpendicular to this y model here, this little vector here. So here you go. So that is perpendicular. So that is really interesting that we should know that, right? And we want this to be minimized. So when our approximation that we're going to make based off of our data points is we want to lessen the error between this. So we want to have a better approximation, right, if our error is lower. So since we know that this is perpendicular, what we need to look at is our base vectors. So our base vectors are up here. These are going to be our limiting factors to this error, right? So we know that this error needs to be perpendicular to our base vectors, our initial base vectors, right? And then 1, 1, 1. Right, so they need to be perpendicular to this. So what we can do is we can do a transpose of our design matrix that we made is A. So A, well, I'll just write. So transpose means you rotate it. So we have a 2 by 3 2 by 3 matrix. We're going to do a 3 by 2 matrix. And we're going to have instead of going down by rows, they're going to go down by columns. So 1, 1.8, and 2, and then 1, 1, 1. And then this is A transpose, so it has a T to it. So if we multiply this by our error, so here, this is going to equal 0. And what that means is that means they're perpendicular to each other. So since we know that A transpose and E are perpendicular to each other, we can solve for this. So that is our equation we're going to be using. So A transpose times our error equals 0. So what exactly is our error, right? So our error is the difference between the data that we were given, our y data that we were given, minus the y model, so the model that we are making itself, right? So error is equal to y data minus y model. So we're going to plug that in for that. So A transpose is equal to y data minus y model is equal to 0. So we already have made y model, so we know what y model is. So A transpose is equal to y data minus A times C. So then we're just going to distribute the A transpose, and then we're going to solve for it on both sides. So get one y data on one side and AC on the other side. So AT is y data equal to 8. Okay. So with this, we can use that to approximate our y model. Thank you. Hello, I'm Gabrielle. I'm going to be doing homework part A, part 2 and 3. So it says from the data set artificially generated with a 21 x values equally spaced between 0 and 10, with generating a slope and an intercept of 2 and 1 respectively, and then populating a normal distribution noise of a standard deviation of 0.75 using the relationship derived in part A1 to obtain the regression slope intercept. And then we're going to graphically compare the artificial data set to the linear model. Okay. So the first thing that we want to do is we're going to import NumPy as empty. And then from plotly.subplots, we are going to import make underscore subplots. So we were given in our problem that we want a data set for our x values to be from 0 to 10, and then we want them equally spaced. So we're going to use np.linespace, and we're going to start out our value with 0 and 10, right? It's going from 0 to 10. And then this last value here is how many spaces you want equal distance between those 2 points. So that's 21. And then we have an equation. They said they wanted a slope of 2 and an intercept of 1. So that's good. And then what would this data is going to give us? This is going to give us a straight line, right? This is going to give us a straight line because this is just a straight line. It's going to give us data, but this data will be artificial. So to kind of mess up the data or to make it more realistic to what real world is going to be like, we are going to add some random numbers in there. So we're going to add some random numbers in our y. So to do this, we're going to do y is y plus np.random. So in np.random, you can use a normal distribution. So we have normal here. So we're going to do local is equal to 0. And then size is going to be our standard deviation. And it was given to us in the problem is equal to 0.75. And then the next thing that we want to do is our size. It's going to be y dot size. We want it to have kind of the same size as y. So shift enter. Okay, so it was scale instead of size. Scale is going to be your standard deviation, not your size. So it's going to keep it in the same size as our y with that size there, but the scale is going to be 0.5, which is our standard deviation. So let's add our subplot. So fig equals make underscore subplots. Okay, sorry. And then from this, we're going to add fig dot add underscore scatter. So x is going to equal x, our y is going to equal our y, and then we're going to have our mode is equal to markers. And then let's do fig dot update underscore layout with 600 height is going to be equal to 400. So let's see what this looks like. Okay, so here is our data. You can see that it's not a perfect straight line of our data, that we have some kind of error in there where it's not completely straight and even. So now the next thing that we want to do is to make our distribution. We want to find the line best fit, right? So to do this, we are going to do is make our design matrix. So with our design matrix, we're going to do A is equal to MP dot concatenate. And so we have is we want to use our x values, and then we want to do MP dot ones like x. So it's going to fill the other side with ones, which is like in the example in the written portion of this problem. So now when we do a t, so this is going to be a transpose multiplied. So in Python, when we multiply two matrices together, we're going to use the add symbol. So when we do our A transpose times our A, it should give us a 2 by 2 side matrix, a 2 by 2 matrix. Okay, so we have that here. So now let's do a t times our y. So this should give us a 2 by 1 matrix. So shift enter. Okay. And then the next thing that we want to do after this is we want to have our vector coefficients, right? Because that is going to help us get our y model. And our y model is going to be the thing that we use to find our line best fit. So C is going to equal our MP dot linear algebra dot solve, and then we're going to have A dot T, so our A transpose times our A, and then we're going to have our A transpose times our Y, and then Control C. Okay, so after we have that, we're going to come back up and we're going to add another figure to this, right? So we have fig dot add underscore scatter, x equals x, y equals, so our y is going to be equal to our A times our C, right? Because this gives our y model. And so our mode, we'll put this in lines, because this is the line best fit. So, let's see. Between these points and this data stat. So that is the end of homework 1, part A.